Hi, welcome to another edition of Calculus 2. The lecture today is going to be about trigonometric substitutions. Let's go take a look at this topic. Here I've written some of the main highlights. Everything revolves around the Pythagorean Theorem. You have seen this thing since middle school. So if one of these quantities is a variable in your integration problem and another one is a constant, then the third one will be one of these type of expressions. Either you are squaring the two legs and finding the hypotenuse, or the hypotenuse is your variable and you're subtracting the constant to find the third side, or the hypotenuse is a constant and one of the legs is the variable. So one of these type of things do show up in a large number of applications. The integrals that contain these expressions can be calculated rather easily with the use of trigonometric substitution. So trigonometric substitution refers to a situation where we are going to consider an angle in this right triangle and express all of these things in terms of that angle. Let's quickly go over some of the main and basic ideas. So three types of expressions show up: sum of two squares, difference of two squares with the variable the first or the variable the second. So in this case we consider a right triangle with A being this leg, x the opposite of the angle, and the hypotenuse will be the exact expression that we are after. So in this triangle, opposite is going to be adjacent times tangent of that angle, so I have this substitution. Taking differential of this, dx is going to be a secant square of theta d theta, because the derivative of tangent is secant. This expression, well, that's the same as the hypotenuse, and we can write it as a times the secant of the angle. Similarly, if you have an expression with x squared minus a squared in radical, in this case we take the x to be the hypotenuse, a will be this leg, theta the angle between the two of them, and the opposite is going to be equal to this expression. Well, what's the relationship between our variable and this angle? You can easily check that. X is equal to a secant of theta. We take a differential, derivative of secant is secant tangent, and this opposite side in this case is going to be the side a times the angle times the tangent of the angle. In the third case, the hypotenuse is a constant and this side is the variable. We take the angle opposite that as theta, and the third side will be equal to this expression. So in this formulation, x becomes equal to a sine theta, derivative of sine is cosine, and the expression that we are after this will be a cosine theta. Okay, we are going to be making use of these substitution very often. One of the set of very important formulas that comes out of this thing, I have recorded them here, so you might have them in your table. We are going to go ahead and do several examples of integrals of this type. Let's start with the very first one of these things. Let's say an integral that is say dx over x squared radical 16 minus x squared. Now we want to do this integral. This is similar to this case, because we have 16 minus x squared, it falls into this category. So this is the picture that we want to have, and we are going to duplicate it. We are going to duplicate it for our case. So I'll draw an example with hypotenuse being 4, this angle, call it theta, opposite of that is like x, and the third side is going to be 16 minus x squared by Pythagorean theorem. we said we take x to be 4 sine of theta. There's a relationship between the opposite, hypotenuse, and the angle. Differential of this thing is going to be 4 cosine theta d theta. And the expression, you can do it one of two ways. Either put the x here, that is 4 sine, and square it and subtract and get 4 cosine, or come here in the picture and see that the adjacent to this angle is going to be 4 cosine theta. So once we have these three, we can complete our substitution. Instead of dx, I have 4 cosine theta d theta. Instead of x squared, I have 4 sine of theta squared, and instead of this radical, I have 4 cosine theta. 4 cosine and 4 cosine cancel out. 4 squared is going to be 16, and this becomes d theta over sine square of theta. Of course, we can also write this thing, and what is 1 over sine square? Yes, that's equal to cosecant square of theta. Well, cosecant square, what's the antiderivative of cosecant square? That is, so you want to make sure you refresh your memory about all those basic formulas from calculus 1. So what is the answer to that? Okay, if you set cotangent, you are the grand prize winner. So this is cotangent of theta plus a constant. Back substitution is quite easy. Cotangent, what is the meaning of cotangent? Ratio of adjacent to the opposite. So we are going to be using all these. So we have minus 1/16 of ratio of adjacent. So that is 16 minus x squared to the opposite plus a constant. So that wasn't that bad. We could handle an integration problem in its original form. It wasn't quite clear what it's supposed to be, but at the end we see it was manageable. Okay, let's go ahead and take a look at some other example. Here is one problem with an additional twist to it. 25x squared plus 4 in radical. You have one of two options here. The issue is that this is not exactly same as what we see in these expressions. Why? Because it's not just x squared, rather it's 25x squared. So one option is to take u to be 5x, and then your problem becomes immediately one of those type of problems you have, or kind of rebuild everything from scratch. Think about, where would such an expression come from? What kind of a triangle should I have? So the idea now is that we are gonna try to imitate this idea from scratch in our problem, as opposed to using two sets of substitution. So here's my question for you. Think about the right triangle. What kind of quantities should I assign to these sides so that somebody in this triangle will be this square root? Okay, think about it 2 minutes, maybe 1 minute. What should I have on my sides such that that type of expression shows up? Well, obviously I need to have a 2 here, so the square of it is 4. I need to have 5x here, so square of it is 25x squared, and then the hypotenuse will be exactly what I'm after. So that's going to be 25x squared plus 4. So in any problem where you have such a setup, this kind of expression shows up. And if you are doing an integration related to this hypotenuse, then it makes sense to perhaps go after a trig substitution. So we say, okay, let's take this one to be theta. If I take that theta, then what can I say about theta and these two sides? Well, obviously tangent of theta is 5x over 2. Well, I really need x, straight out x. What's x? Well, that's going to be 2/5 of tangent of theta. Okay. Well, I need to substitute for dx as well. Now, who is dx? Dx, well, this is a factor, 2/5. What's the derivative of tangent? So, well, what is the derivative? Yes, quickly. Secant square of theta d theta. What else do I need to substitute? Well, I need to substitute this thing. 25x squared plus 4. Well, you can plug this thing here and clean it up and apply a trig identity, or alternatively you can come to this picture and say, well, how can I connect this to this angle? Well, I need a third side as well. Let's go after this one. So suppose I want to write what connection do I have between these three? Either you have to use cosine of theta or the secant of theta. Let's go straight to secant of theta. Who's secant? Ratio of hypotenuse to the adjacent side. So secant of theta is 25x squared plus 4, that's hypotenuse, divided by the side that is 2. So this radical would be 2 times secant, 2 times secant. So we are ready because I can substitute everything. So I have here, instead of dx, I have my 2/5 of secant square of theta divided by, clean this up, the radical became just plain 2 secant of theta, and dx became 2/5 of secant square of theta d theta. Well, sorry, I duplicated myself. Sorry, let me make a correction. Let's write it again. Dx, I had already written it. Dx is 2/5 of secant square of theta d theta. So that's what I meant to write. And the radical in the denominator is just 2 secant theta. Well, when we simplify it, these numbers becomes 1/5. I can take it outside. Ratio of these two is just secant of theta d theta. What is the antiderivative of secant? One of the slightly more tricky problems in calculus 1. Do you remember what that was? We come across this thing a few times. Let me get you started. Logarithm of what? What do I have in my absolute value for this? We have logarithm of, just think about it a second, of course, secant of theta plus tangent of theta and a constant. So 1/5 of logarithm of. Now secant of theta, thankfully I have it here, right? So I just write 25x squared plus 4 over 2. Tangent, well, I have it here. That is fortunate that we have them. Plus a constant. This is perfectly good. If you want to clean it up a little bit more, maybe you want to take a common denominator, so it's a 2, and then you have radical 25x squared plus 4, and then a 5x. Can you think about the simplification here? What can we do to simplifying here means kind of using the least amount of ink to write the final answer. So you what about the logarithm of ratio? Do you remember from pre-calculus? What's a logarithm of a over b? I don't need it. Well, logarithm of numerator. What's the next piece? Of course, minus logarithm of denominator. So I don't know what this b is doing here. So 1/5 of logarithm of numerator 25x squared plus 4 plus 5x. Well, and then I have to subtract logarithm of 2 plus a constant. Well, 1/5 of logarithm of 2 subtracted from this constant will be some other constant. So I might as well merge my constants, and then so this is so combining these constants I can write something else. Any other simplifications that comes to your mind? Let me see if I can encourage you to think about this thing for a second more and tell me what other thing can we do to clean this expression as much as we can clean it. As much as we can clean it. We want to reduce the amount of operations. One thing about this absolute value, do I absolutely need that absolute value? Do I really need the absolute value? Well, you put absolute value if you want to convert something that's negative into positive. But does this thing have a chance of becoming negative? I claim no. This thing is never negative. Can you supply a reason why this thing is never negative? So you don't really need to take an absolute value. Why is that? Because 25x squared, well, this is positive. You're adding something to that. This square root is going to be more than 5x. So the 5x can never make this radical, cannot never make this sum to become negative. So if you wish, you can do away with the absolute value. Just put a parenthesis instead, or just remember this whole thing is one single piece. You don't need to take absolute value with it because it's always positive. So now our problem, we have the final answer, and it's as clean as it can be. Now let's do perhaps one problem where there is a limit of integral, and then we want to learn how to handle these type of problems. We have a couple of ways of handling these type of problems. Suppose I want to integrate, say, from 3 to 4 of here an expression I have, say, x squared minus 5 over x dx. Notice that I'm putting a number here is not a complete square, so we are taking the kids' gloves off a little bit. So every now and then you have to be willing to live with problems that have square roots in them. This is one such problem. So again, we have this expression. Let me see if you can invent the problem for yourself, invent the substitution for yourself. What's the rationale behind the formulation we gave at the beginning? So we want to have a right triangle to motivate this square root. Well, who should be x in this situation? Who should be the x so that we will have an expression like square root of x squared minus 5 in it? Who should be x? This is a very crucial thing. So I want you to think as long as it takes, think about it. But it's hopefully at the end of this lecture is going to be immediate to you. Well, if you are taking difference, then the first one has to be your hypotenuse and the other one has to be square of one of the legs. So x has to be this, and square root of 5 can be either of these. By convention we take this one. Okay, so then what would be the opposite? Opposite is going to be square root of this minus square of that. Square root goes away. We take this one to be our angle. Okay, so that's where the picture comes from. So we'll have x is equal to, we connect these three things to each other, so it's going to be square root of 5 times secant of theta. Well, then what is my dx then? My dx, take this is a number, derivative of secant is going to be what? Secant tangent d theta, and then of course the main attraction is that radical. What is that radical? Well, connect this and the angle and your constant. What's the connection? Of course it is the adjacent times the tangent of this. So radical 5 times tangent of theta is equal to the opposite. So I have my picture complete here. Now you have two options. One is set these things aside, complete the integration, and then come back at the very end, substitute your x by 3 and 4, and you are done. So that is one way, which is like come to the bottom of the problem when you have the final answer and replace your x's by two limits, and then you're done. There's an alternate way that's a little bit more interesting, a little bit cleaner. The way we think about this thing is that when you want to do a substitution, do a complete substitution. That is, not only substitute x with the theta, but these two have to be replaced by specific values of theta, like initial value and a final value of theta. Meaning what? Meaning consider this problem when x is 3. So let's suppose this is the situation where x is 3. This is radical 5, and then therefore this is x squared, which is 9 minus 5, and this is some angle. Let's call this thing angle 1. And then theta changes. This angle increases until x goes from 3 to 4. So now x has become bigger. X is equal to 4. This is still radical 5. By now, this third side has become square of 4, which is, that's right, 4 squared minus 5. Here I made a mistake. Let me correct my what I read here. This is, of course, 3 squared minus 5. It's 4 squared minus 5. Here, well, is my final value of theta. Let's call it theta 2. So my integral now, my radical becomes radical 5 tangent of theta. X is radical 5 secant of theta. Dx is again radical 5 secant of theta tangent of theta d theta. This is all exactly as before. Now these two numbers can be replaced by whatever angle number 1 is and whatever angle number 2 is. So we are going from here to here. Then I clean up. Radical 5, radical 5, radical 5. One of them survives. Secant cancel. I have tan squared d theta. Okay, we have learned in the previous section how to handle this. How do I integrate tan square? It's actually from calculus 1. Well, easiest thing, write it as secant squared minus 1. Tan squared, secant squared minus 1. Why do that? Because antiderivative of secant, that is, we know what it is. What's the antiderivative of secant, you say? Okay, you have to be very quick with these things. What's antiderivative of secant? So have that table in front of you, go back and forth until everything becomes second nature. So this is tangent of theta. And then antiderivative of 1, well, that's the easiest thing in the world, theta. Now we have theta 1 and theta 2. So what is that? So let's go ahead. Maybe I squeeze it here. Radical 5 times, I have two pieces. One is tangent of theta, sorry, let me write it better. Tangent of theta 2 minus tangent of theta 1. Then minus theta 2 minus theta 1. Okay, we are all done. Radical 5 of tangent of theta 2. Tangent of theta 2 is ratio of opposite to adjacent. 4 squared minus 5. Let's clean this up a bit. It's radical 11. So this is radical 11 over radical 5. Tangent of theta of 1, 3 squared minus 5. It's radical 4, or clean it up as 2. So it's radical 4 over radical 5 minus, now angle theta to itself. How do I calculate angle? It's the inverse tangent of the ratio. So I write tangent inverse of just exactly that number, radical 11 over radical 5, and then minus what? Same thing here, tangent inverse of, this one is radical 4 over radical 5. Okay, that's our answer. If somebody wants it with so many decimal places, you crank up your calculator and find it. If you want to clean it up a bit, radical 5 cancels these things in the denominator, so radical 11 minus radical 4 minus, here we don't have much simplification, write it like this maybe, in this case 4 accidentally comes out of radical, but in general it just stays there. So we have seen many of these integrals now. We can do integrations by trig substitution. Again, let's remember what was the moral of the story. In many physics engineering applications, you have to calculate the distance. That's the most primary thing. If you have a variable, then you end up with one of these three radicals. So these type of things do show up in applications quite often. It's one of these three possibilities, and then we can do our substitution accordingly. Three perhaps more famous example of these things are these very basic type of integrals. You can perform it with the same style that we have done, and I leave that exercise to you. So until next lecture, good luck and